Okay, let's just jump right in. Have you ever wondered what exactly turns a standard language model into a reasoning machine like GPT-4 or Claude 3? Well, the secret sauce is this algorithm called Proximal Policy Optimization, or PPO. It is the absolute key that unlocks complex reasoning. But, the original paper it's a bit of a beast. So today we're going to break PPO down from the ground up so you can see exactly how it works.
So this is really the central question, isn't it? How do you go from a simple text predictor, something that's basically just good at guessing the next word, to an engine that can actually reason and follow these super complex instructions we give it?
On one side, you've got your standard large language model. Its only job is to predict the next word. But over on the other side, you have an aligned LLM. This is the model that can solve math problems, write code, follow all those subtle instructions. The bridge, the thing that gets you from here to there, is a process called alignment. And PPO is the algorithm that makes that alignment happen. To really get a handle on PPO, we first have to talk about the basics of reinforcement learning. And honestly, the best way to do that is to just forget about language models for a second and think about a robot. Let's start with something simple, like a Roomba. And what's so powerful here is just how perfectly these ideas translate. In reinforcement learning, you always have an agent taking actions in a state to get a reward. For a Roomba, the agent is the robot. Its action is to move. The state is its location in the room, and the reward? Maybe it's how much floor it's cleaned. Now for an LLM, the agent is the model itself. The action? That's generating the next word, the next token. The state is all the text it's written so far. And the reward? Well, that's where things get interesting. Let's make this super concrete with a math problem. The model gets a prompt, right? And it starts generating an answer, one token at a time. Each token it spits out is an action, and each action creates a brand new state, which is just the prompt plus all the text it's generated so far. This goes on and on until it gets to a final answer. But look closely. It only gets a single reward, a +1 for getting it right, at the very, very end of this whole long process. And that right there, that brings us to our first huge problem. How can one single reward, at the end of a long chain of actions, possibly be a useful learning signal for every single step? How do you tell the model that the first word it chose was great, but maybe the 10th one sent it down the wrong path? We need a way to create a learning signal for every single action. The solution is this really elegant concept called the advantage. Just think of it as a little score for each individual action, for every token the model generates. And all it does is answer one simple but powerful question. Was generating this specific token better or worse than the other choices I could have made right here? This one idea explodes that one big reward into tons of tiny, targeted learning signals. So here's the core of it. This advantage score becomes the magic multiplier in our loss function. That's just the equation the model uses to learn. The entire goal is to boost the probability of actions that had a high advantage score. We're literally multiplying the probability of taking an action by how good that action was. The whole game from here on out is just figuring out a really good, really reliable way to calculate that advantage number. And this is where modern reinforcement learning gets really clever. Instead of trying to make one model do everything, we're going to use two. It's an architecture called app², and it's how we're going to get a great estimate of our advantage. It's really just a simple division of labor. You've got the actor, that's our main LLM, the one that's actually doing the work and picking the next word, and then you have the critic. This is a second, totally separate model, and its only job is to be a judge. It looks at the sentence so far, the state, and it predicts how good that state is. It's essentially guessing the future reward from that point on. Okay, so to calculate the advantage, we kind of have two extreme options. We could just wait and see what the real final reward is. That's called the Monte Carlo method. It's super accurate, but it's also really noisy. One random good or bad result can totally throw off your training. The other option? We could just trust the critic's guess about the future reward. That's called bootstrapping. It's way more stable and less noisy, but it's biased. Because, the critic might be wrong. This is the classic bias-variance trade-off. And this leads to this beautiful, elegant solution, generalized advantage estimation, or GAE. Instead of picking one of those extremes, GAE basically says, why not use both? It cleverly combines them by calculating an exponentially weighted average of all the possible estimates. It gives more weight to the real rewards that are close by and trusts the critic more for things far off in the future. What you end up with is a signal that is both stable and accurate, the best of both worlds. Okay, so we have a really solid way to calculate our advantage. We're done, right? Well, not quite. There's another huge problem we've got to solve: efficiency. I mean, why would you ever want to throw away perfectly good data? So the system we've described so far is what's called on policy. And what that means is we generate a whole batch of responses, we use them for one single update to the model, and then we throw them all in the trash. It is painfully slow and inefficient, especially when you compare it to supervised learning, where you might train on the same data set for hundreds of cycles. The fix for this is a neat mathematical trick called importance sampling. It's what lets us reuse that old data for multiple training steps. And it all works by applying a simple correction factor, which is this ratio you see here. The probability of an action under our new updated model divided by the probability under the old model that actually generated the data. So reusing data is amazing for efficiency, but it opens up a brand new and honestly a pretty dangerous problem. What's to stop the model from changing way too much, way too fast? If that new model becomes very different from the old one, that ratio we just talked about can explode or go to zero, leading to these massive, totally unstable updates that can just completely destroy the model. And this is finally it. This is where proximal policy optimization, PPO, makes its famous, brilliant contribution. This is the final piece of our puzzle. The core idea behind PPO is just beautifully simple. All it does is clip the ratio. That important sampling ratio we just introduced, it's forced to stay within a really narrow window, something like between 0.8 and 1.2. That's it. It just acts as a safety rail, physically stopping the model update from ever getting too big. Let's just walk through how this works in the math. So first, you calculate the normal update, your ratio times the advantage. Second, you calculate a clipped version, where that ratio is clamped inside that small window. And then, this is the magic trick, you just take the minimum of those two values. This simple min function makes sure the model learns normally when the update is small, but it gets cut off, clipped, if it ever tries to take a dangerously large step. And that's really the key takeaway here. For years, the holy grail of reinforcement learning was just making the training process stable and robust. And people tried all these complex mathematical solutions, but it was PPO's dead simple clipping idea that was the practical, elegant solution that finally just worked. It wasn't the most complicated idea, but it was the one that was reliable enough to build today's models on. Which kind of leaves us with this one last fascinating thought. If a simple, almost shockingly elegant trick like clipping a ratio can be the key to aligning these massive language models and unlocking their ability to reason, what other simple ideas are still out there, just waiting to be discovered that could unlock the next level of AI?